At 7:42 on the morning of March 14, 1941, Beatrice Schilling stood on the cold tarmac at RAF Kendley. She was 32 years old, an engineer for the Royal Aircraft Establishment, and she was watching a young Hurricane pilot climb into his cockpit for what might be his last mission. For 6 years, Schilling, known as Tilly to her colleagues, though never to her face, had been a scientific officer at the RAE, the Corps Research and Development Agency for the Royal Air Force. On that March morning, she was the RAE's principal technical officer for carburetor research, and she was facing a problem that was killing her pilots. She had 0 solutions, at least 0 authorized solutions. The war in the air was a brutal calculus of machine versus machine, and Britain's math was failing. The Luftwaffe had sent 43 Messerschmitt Bf-109 fighters across the Channel that week alone. RAF pilots had engaged them in 27 separate dogfights. The cost was staggering. 14 Hurricanes had gone down, 9 Spitfires. And the pattern, detailed in the after-action reports that landed on Schilling's desk, was always the same. A British pilot spots a German fighter. The British pilot pushes the stick forward, bunting the nose of his Spitfire or Hurricane into a steep, aggressive dive to attack. And his engine cuts out. Not a sputter. A complete, terrifying silence. The propeller stops windmilling, and the pilot is suddenly flying a multi-ton glider. In the 1.5 seconds of mechanical failure, the German fighter either escapes or worse. The Bf-109 pilot, seeing the stalled British plane, circles back. He puts cannon shells through the helpless aircraft while the RAF pilot fights desperately, not the enemy, but his own Rolls-Royce Merlin engine, struggling to get it to restart. This was the crisis Beatrice Schilling was sent to solve. She had seen the combat reports. She had read the maintenance logs. She had interviewed the haunted-looking pilots who had survived the engine failures. And she knew the cause. It wasn't enemy action. It was the carburetor, a simple catastrophic flaw in fluid dynamics that occurred during negative G maneuvers. Simple physics, brutal consequences. The problem was a 2-stage phenomenon, a cascade of mechanical failure that began the moment the pilot pushed the stick forward. Early Merlin engines were fitted with a float-type Skinner's Union, or SU, carburetor. This device, much like the cistern in a household toilet, relied on gravity and buoyant float to maintain a constant fuel level in a small reservoir called the float chamber. This reservoir fed fuel into the engine through a series of small outlet holes or jets located at the bottom of the chamber. Stage 1 was fuel starvation. When a Spitfire pilot pitched his nose steeply down, he and the aircraft experienced negative G-forces. The laws of inertia took over. The liquid fuel inside the float chamber was instantly thrown toward the top of the chamber, away from the jets at the bottom. For a precious, fatal 1.5 seconds, the jets sucked in nothing but air. The engine, starved of fuel, would fluff or weak cut. A momentary, terrifying hesitation. But Stage 2 was the killer. If the negative G dive was sustained, the float mechanism itself failed. With all the fuel at the top of the chamber, the float, no longer buoyant, dropped to the floor. This action signaled to the carburetor that the chamber was empty. In response, it fully opened the main needle valve, demanding fuel. The engine's fuel pump, operating under pressure, obliged. It rammed pressurized fuel uncontrollably into the float chamber, overwhelming the system. This rich cut drowned the supercharger in an excessively rich mixture, stalling the engine completely. The Germans didn't have this problem. Their Daimler-Benz DB601 engines, which had been in service since 1937, used a sophisticated direct fuel injection system. There was no float chamber, no reliance on gravity. Injection pumps kept the fuel at a constant pressure, delivering it straight into the cylinders regardless of the aircraft's attitude. The difference was like trying to drink water from an open glass while riding a roller coaster versus drinking from a pressurized water bottle with a pump. One spills and fails. The other delivers a consistent stream. The Bf-109 pilots could dive, climb, roll, or fly inverted without their engine missing a single heartbeat. They knew about the British flaw. It gave them a decisive advantage in every single engagement. Luftwaffe pilots developed a specific tactic called the bunt, a sharp -G pushover to escape any pursuing RAF fighter. The British pilots, forced to use a time-consuming countermeasure of performing a half roll to invert their aircraft before pulling back on the stick to dive, could only watch as their prey escaped. Squadron commanders reported it with increasing desperation. The Royal Air Force was bleeding experienced pilots faster than training schools could ever replace them. The engineer Ernest Hives at Rolls-Royce would later note with grim honesty that this single defect had saved the lives of many enemy pilots who escaped to fight another day. Schilling had spent 11 agonizing months working on the problem. The engineering teams at Rolls-Royce were, of course, designing a proper solution, a complete redesign of the fuel delivery system, a Bendix pressure carburetor that would eliminate the float chamber entirely. But that was a complex, ground-up solution. The pressure carburetor wouldn't be ready for mass production until 1943, maybe 1944. The war wouldn't wait. The pilots couldn't wait. Every morning, young men, barely out of their teens, climbed into Spitfires and Hurricanes, knowing that their own engines might kill them before the Germans ever got the chance. Squadron leader Davies walked past Schilling toward the waiting Hurricane. He was 24 years old, with 41 combat missions and 3 confirmed kills to his name. He had reported catastrophic engine failure twice in the past month, both times during combat dives. Both times he had survived by pure luck and 3,000 hours of training. He nodded at Schilling. She nodded back. He didn't know who she was. He didn't know she was the carburetor specialist from the RAE at Farnborough, the single most knowledgeable person on Merlin fuel systems in the country. He probably thought she was someone's secretary, a WAF administrator. She was, after all, a woman, and this was 1941. But Schilling had brought something with her to Kenley that morning. Tucked away in her leather satchel was a small brass component, precisely machined, simple beyond belief. Her small team at the Royal Aircraft Establishment had tested it on a bench engine for 6 weeks. On the ground, it worked. But bench tests weren't combat. Combat was 300 miles per hour. Combat was negative G-forces strong enough to pin a pilot against his harness. Combat was life or death in 1.5 seconds. Schilling walked to her Norton motorcycle parked near the dispersal hut. In her satchel was the brass restrictor and a plan that would either save the Royal Air Force or end her career at Farnborough in disgrace. By noon, she'd know which. The carburetor problem had become a full-blown crisis in July 1940. The Royal Air Force had just switched to high-grade 100-octane fuel. This new fuel meant more boost could be run through the Merlin engine. More boost meant a sudden leap in power, from 1,100 horsepower to 1,310. The Spitfire Mark II could now hit 370 miles per hour in level flight, fast enough to finally catch the Messerschmitt 109s. But the engine's Skinner's Union carburetor, designed for a different time, couldn't handle the extreme negative G-forces that came with high-speed combat maneuvering. Beatrice Schilling understood carburetors better than anyone at Farnborough. She had been recruited by the RAE in 1936 after earning a bachelor's degree in electrical engineering from Manchester University, where she was one of only 2 female students. She had first been employed by an electrical engineering company run by a woman, Margaret Partridge, who had actively encouraged her academic path. After Manchester, she earned a Master's of Science in Mechanical Engineering. But her real education hadn't come from a university. It came from the garage. She had demonstrated a profound mechanical aptitude from childhood. At 14, she bought her first motorcycle, a Norton. She hadn't just learned to ride it. She had stripped the 2-stroke engine down to its individual components, learned how every single part worked, and then rebuilt it herself. By the time she was 25, she was racing that same Norton at the legendary Brooklyn circuit. She lapped the track at an average speed of 106 miles per hour, fast enough to earn the British Motorcycle Racing Club's Gold Star. Only 3 women in history had earned that award. Schilling was the second. She even, so the story goes, refused to marry her fiancé, George Naylor, until he also proved his mechanical and racing skill by earning his own Brooklyn's Gold Star. That racing experience had taught her something university labs never could. It taught her how engines failed under extreme stress. High G turns, sudden acceleration, extreme lean angles. Her hands-on experience tuning her own bike, experimenting with fuel-air mixtures, and the length of inlet tracts gave her an intimate, intuitive knowledge of how engines breathed. She learned to feel what an engine needed before the gauges ever told her. When she joined the RAE, she was first placed in the Technical Publications Department, a tedious role she loathed. After 8 months, she forced a transfer to the Engine Department. By November 1939, 1 month after war was declared, she was promoted to Principal Technical Officer, in charge of all carburetor research and development. She was one of only 2 women in the entire department. The other was a secretary. Most of the men she worked with had never met a female engineer. Some of them didn't believe women belonged in engineering at all. Schilling didn't care what they believed. She cared about keeping pilots alive. And now, British pilots were dying because their carburetors couldn't handle combat stress. The solution had come to her in January. It was, like the problem, simple physics. The fatal rich-cut flooding happened because fuel could flow unrestricted when the float valve malfunctioned. What if you simply restricted the flow? Not completely, just enough to prevent the catastrophic flood. The engine would still get fuel, just not too much fuel. The idea was a small brass disc with a precisely calculated hole in the center, installed in the fuel line before the carburetor. This disc would limit the maximum fuel flow to a volume only slightly less than what the engine demanded at full throttle. She'd gone into the RAE workshop and machined the first prototype herself. It was shaped like a small brass thimble, 0.125 inches in diameter. The hole in the center was 0.04 inches. Those dimensions were everything. Too large, and the carburetor would still flood. Too small, and the engine would be starved of fuel at full power, a fatal flaw in itself. She'd tested 17 different sizes before finding the perfect balance. Then she'd simplified the design. A thimble was hard to manufacture. A flat washer was easy. Easier to manufacture, easier to install, easier to replace. Bench tests showed it worked. The restrictor prevented the flooding during simulated -G conditions. It didn't, however, fix the initial weak cut, the 1.5-second fluff from fuel sloshing away from the jets. That problem was inside the float bowl, and the restrictor was outside it. But Schilling wagered that pilots could survive a 1.5-second hesitation as long as it wasn't followed by a complete engine stall. But bench tests weren't combat. She needed to test it on an actual aircraft, under actual combat conditions. The problem was getting permission. Installing unauthorized modifications on RAF fighters violated about 40 different regulations. It bypassed all standard airworthiness checks. If the restrictor failed in combat, if it did starve the engine at full power, or if the welding broke, or if any one of 1,000 things went wrong and a pilot died, Beatrice Schilling would be court-martialed. She would be imprisoned. She decided to skip permission and ask for forgiveness later. That morning at Kendley, she had 6 restrictors in her satchel and one very cooperative ground crew sergeant who owed her a favor. Sergeant William Cooper had worked on Merlin engines for 3 years. He had seen 19 pilots from his station die from engine failures. He didn't ask questions when Schilling, the quiet, serious woman from Farnborough, showed him the small brass washer and explained what it did. He just nodded and reached for his toolkit. The Hurricane sat on the dispersal pad. Squadron Leader Davies was inside, engine warming up. 20 minutes until takeoff. Cooper worked fast. He disconnected the fuel line between the pump and the carburetor. The restrictor, small and unassuming, slid into place. Cooper, a master of his craft, welded it with a small butane torch. 60 seconds of work. The modification was completely invisible unless you knew exactly where to look. Schilling checked the weld. Clean, solid, professional. Squadron Leader Davies would fly with the restrictor. He didn't know it was there. Schilling hadn't told him. She hadn't told the squadron commander. She hadn't told anyone except Cooper. If the restrictor failed and Davies died, there would be no paper trail. No authorization forms, no testing documentation. Just a dead pilot and a brass washer that shouldn't have been there. The Hurricane's Merlin engine roared to full power. Davies ran through his pre-flight checks. Oil pressure good. Coolant temperature good. Magnetos firing on all 12 cylinders. He released the brakes. The Hurricane rolled forward, gathered speed, and lifted off the grass. Schilling watched it climb. 800 feet, 1,200 feet, 2,000 feet. The Hurricane banked south toward the channel. She'd brought a pair of binoculars. She watched Davies climb to 15,000 feet. 2 more Hurricanes joined him. A section of 3, standard patrol formation. They flew toward Dungeness. German fighters had been active over Dungeness all week. If Davies encountered a Messerschmitt, he would have to dive, and the restrictor would either work or it wouldn't. Schilling waited on the tarmac. Cooper stood next to her. Neither of them spoke. Around them, the fighter station continued its business. Ground crew prepared 2 more Hurricanes for the afternoon patrol. A fuel truck rumbled past. Mechanics shouted technical jargon across the dispersal area. The normal sounds of a fighter station at war. Schilling heard none of it. She was calculating fuel flow rates in her head. 0.04 inches. Maximum flow at full throttle. Negative G duration 1.5 seconds. The math worked. But math wasn't combat. 40 minutes passed. An hour. Radio silence from Davies' section. That could mean anything. No contact with enemy fighters, or contact so intense there was no time to report. Or Davies was dead, and his Hurricane was a smoking crater in a French field. At 09:37, the radio in the dispersal hut crackled. The controller's voice. 3 Hurricanes inbound, 2 minutes out. Schilling raised the binoculars. Her hands were shaking. She saw them. 3 dark shapes against the morning sky. All 3 aircraft, no losses. The Hurricanes entered the circuit. Davies landed first. He taxied to dispersal, cut the engine, and climbed out. Schilling walked toward him. She'd designed bombs before. She'd tested engine modifications under sterile laboratory conditions. She'd never done anything like this. Never installed an unauthorized component and sent a man into combat to test it. Davies pulled off his leather helmet. He was smiling. That was unusual. Pilots didn't smile after combat patrols. They usually looked exhausted, haunted. Davies looked excited. Sergeant Cooper, walking up behind her, asked the question she couldn't. "Any problems with the engine, sir?" Davies looked at Cooper, then at Schilling, then back at Cooper. "Best the Merlin's ever run," he said. He dove on 2 Messerschmitts over Dungeness. The engine, he said, never missed a beat. Schilling asked him to describe exactly what happened. He'd spotted 2 Bf-109s at 14,000 feet flying east toward France. Davies had positioned his section above them, holding the altitude advantage. He had pushed the nose forward into a steep 400-mile-per-hour dive. He felt the negative G-forces lift him against his harness straps. The exact maneuver that should have killed his engine. But the Merlin kept running, full power, through the entire dive. Davies had closed to 200 yards before the German pilot even saw him. He'd fired a 3-second burst, saw strikes on the left Messerschmitt's wing route. The German fighter broke hard right and fled toward France. Davies had pulled up, climbed back to altitude. The engine, he reported, had performed flawlessly. It was the first time in 11 months that he had successfully pressed a diving attack without his engine cutting out. He wanted to know what maintenance had done to his Hurricane. Schilling told him. She explained the restrictor, the small brass washer, the fuel flow limitation. Davies stared at her for 5 seconds. Then he turned to Sergeant Cooper. "Put that thing in every Hurricane on this station," he said, "today." Schilling explained it wasn't authorized, that it was an unapproved RAE test. Davies didn't care about authorization. He cared about surviving combat. Every pilot at Kendley had lost friends to engine failures. 19 pilots dead in 6 months from this one squadron. Davies said if the brass wanted to court-martial him for installing an unauthorized modification, they could do it after the war. Right now, his squadron needed working engines. Act as a professional narrator for a long-form historical documentary. Your primary goal is narrative continuity. You are reading one segment of a much longer script. Therefore, you must avoid dramatic conclusions or a finality tone at the end of the text. Instead, maintain a steady, neutral, and forward-moving pace, as if you are about to continue reading the next sentence. Voice quality. Maintain a deep, confident, and clear voice. The style should be authoritative and engaging, like a high-quality historical podcast, but prioritize consistency over excessive drama. Do not slow down significantly or drop your pitch at the end of the segment. Your job is to make all the short audio segments sound like they were recorded in one single continuous take. Schilling installed restrictors in 4 more Hurricanes that afternoon. Schilling had brought 6. She kept 1 for testing. 5 Hurricanes flew combat patrols with restrictors over the next 3 days. The reports were unanimous. 0 engine failures. 12 diving attacks successfully pressed against German fighters. Pilots reported the Merlin engines ran perfectly. Word spread like fire. By March 18th, every squadron commander in 11 Group knew about the fix from Farnborough. They wanted it, all of them, immediately. Schilling's office at the RAE received 14 phone calls in 2 days. Could she come to their stations? Could she bring more restrictors? How fast could they be manufactured? The problem was supply. Schilling had machined 6 restrictors herself in the RAE workshop. Manufacturing thousands would require proper production facilities, brass stock, precision machining equipment, and quality control. She needed approval from the Air Ministry. She needed funding. She needed time. She got approval in 4 days. The unauthorized test at Kenley had proven so undeniably successful that it cut through all bureaucracy. The Air Ministry fast-tracked her proposal. They called it a war-winning modification. Rolls-Royce received the production contract. They could manufacture 500 restrictors per week. Installation would begin immediately at every fighter station in Britain. Schilling assembled a small team, 3 engineers from Farnborough, 2 civilian mechanics. They would tour the RAF stations and oversee the installation. The restrictor could be fitted without removing the aircraft from service. That was critical. Every Hurricane and Spitfire needed to stay operational. The Battle of Britain was technically over, but German fighters still crossed the Channel daily. RAF Fighter Command couldn't afford to ground its squadrons. Schilling loaded her Norton motorcycle with tools and the first batch of restrictors. She'd visited 43 RAF stations before the war. She knew every fighter base in southern England. She knew the commanding officers. She knew the ground crews. Now she'd visit them again, this time with a brass washer that would save their pilots. By March 25th, the installation teams were ready. 600 restrictors were manufactured. 40 stations were on the schedule. 3,000 Merlin engines were waiting for modification. Schilling started her Norton and headed north toward Biggin Hill. Biggin Hill was the busiest fighter station in 11 Group. 32 Spitfires, 21 Hurricanes, 4 squadrons rotating through continuous combat operations. Schilling arrived at 0800 on March 26th. The station commander, Group Captain Grace, met her at the gate. He had lost 7 pilots to engine failures in the past 2 months. He wanted the restrictors installed immediately. The ground crews worked in shifts, 4 aircraft at a time. Each installation took 12 minutes. Disconnect fuel line. Weld restrictor in place. Reconnect line. Test for leaks. The welding had to be perfect. A faulty weld at altitude, under pressure, could starve the engine completely. Schilling supervised every single installation personally. She checked every weld. She tested every connection. She rejected 3 restrictors from the first batch that didn't meet her exact specifications. Pilots watched the modifications with intense interest. Flight Lieutenant James Lacey, who had 41 combat missions, had experienced engine failure twice. He asked Schilling how a simple washer could solve such a complex carburetor problem. She explained fuel flow physics,
float chamber dynamics, and the negative G effects on liquid fuel. Lacey, an engineering graduate from Cambridge, understood immediately. He called it brilliant simplicity. By March 28th, all 53 Merlin engines at Biggin Hill had restrictors installed. Schilling moved to Hornchurch, then Northweald, then Tangmere. The pattern repeated at every station. Ground crews worked 12-hour shifts. Pilots flew combat patrols with the modified engines. 0 failures were reported. The restrictor worked exactly as designed.
Pilots, with their gallows humor, started calling it Miss Schilling's Orifice. The nickname was reportedly coined by Sir Stanley Hooker, the chief engineer at the Rolls-Royce Supercharger Division. It was crude British humor, slightly inappropriate. Schilling didn't mind. She'd spent years working with RAF personnel. She understood how military men dealt with stress. If crude nicknames helped them remember the modification and trust it, she'd accept any name they wanted to use. The nickname spread faster than the restrictor itself. By April, every pilot in Fighter Command knew about Miss Schilling's Orifice. They requested it specifically. Some pilots, hearing of its success, refused to fly combat missions until their aircraft had the modification installed. Squadron commanders supported them. They had seen too many good pilots die from a preventable engine failure. Act as a professional intelligence, an ocean of data collectors noticed the change. Luftwaffe after-action reports from early April began to mention, with confusion, improved RAF diving attacks. British fighters no longer broke off pursuit during negative G maneuvers. Messerschmitt pilots could no longer exploit the carburetor weakness. Der Bund escape maneuver had suddenly, inexplicably, stopped working. The tactical advantage had disappeared. By mid-April, Schilling's teams had installed restrictors in 2100 Merlin engines. Every Hurricane and Spitfire in Fighter Command, every operational training unit, every aircraft in reserve status. The modification became standard equipment. New aircraft rolling off the production lines at Castle Bromwich and Southampton came with restrictors pre-installed. The pressure carburetor, the proper solution, was still in development. Rolls-Royce estimated it would be ready in 1943. But the restrictor worked so well that some engineers questioned whether the new carburetor was even necessary. Why redesign the entire fuel system when a simple brass washer solved the problem? Schilling knew the answer. The restrictor was a stopgap. A brilliant stopgap, but temporary. It only fixed the fatal rich cut. The 1.5-second weak cut fluff remained. The pressure carburetor would eliminate the problem completely, using fuel injection principles similar to the German engines. No float chamber, no flooding, no hesitation. That was the proper engineering solution. But until 1943, Miss Schilling's Orifice kept RAF pilots alive. And that was enough. The results were measurable. Fighter Command tracked combat statistics meticulously. The numbers told a clear story. In March 1941, before the restrictor, RAF fighters reported engine failures in 38% of diving attacks against German aircraft. Pilots broke off pursuit. Enemy fighters escaped. In April 1941, after the restrictor was widely installed, engine failures during diving attacks dropped to 0.4%, almost non-existent. The kill-to-loss ratio improved immediately. March had been brutal. Fighter Command lost 47 Hurricanes and Spitfires in combat, shooting down 61 German aircraft, a ratio of 1.3 to 1. Barely breaking even. April was different. 29 British fighters lost, 94 German aircraft destroyed,
a ratio of 3.2 to 1. The restrictor wasn't the only factor, but squadron commanders credited it as a major contributor.
Pilots reported increased confidence. Flight Lieutenant Robert Stanford Tuck, a flying ace, had experienced engine failure 4 times before the restrictor. After installation, he pressed diving attacks without hesitation. He destroyed 3 Messerschmitt 109s in May, 2 more in June. He credited the restrictor with giving him the confidence to commit to aggressive tactics. The modifications spread. RAF Coastal Command requested restrictors for their bow fighters. Bomber Command wanted them for training aircraft. By June, Rolls-Royce was manufacturing 1,000 restrictors per week. The restrictor remained in service through 1943. When the new Bendix pressure carburetor was eventually introduced, converting existing aircraft proved to be a problem. It required extensive modifications, removing the old carburetor, installing new fuel pumps, rewiring engine controls. Each conversion took 8 hours. Fighter Command couldn't afford to ground entire squadrons for that long, so they kept the restrictors. Many aircraft flew with Miss Schilling's orifice until 1944, some until the end of the war. New production Spitfires and Hurricanes received the pressure carburetors, but older aircraft kept their little brass washer. Pilots trusted it. Ground crews knew how to maintain it. If it worked, don't change it.
Schilling moved on to other projects. The Royal Aircraft Establishment kept her busy with dozens of technical challenges. She worked on cold-weather starting systems for engines in Iceland and Russia. She researched high-altitude fuel mixture problems. She helped design improved supercharger systems for late-war Merlin variants. But the restrictor remained her most famous contribution. Pilots remembered it. Engineers studied it. After the war, aviation schools taught it as a perfect example of elegant problem-solving under pressure. Simple solution, immediate implementation, measurable results. Everything good engineering should be. Keith Maddock, a chief engineer during the war, said it years later. Beatrice Schilling helped us win World War II. Of that, there is no doubt. The restrictor was a war-winning modification.
Her work didn't stop. The RAE had other critical problems. Engine failures at high altitude, fuel system icing in extreme cold, starting problems in Arctic conditions. Every problem threatened pilot lives. Every problem landed on Schilling's desk. She developed cold start procedures for Spitfires deployed to Murmansk, where Russian winter temperatures dropped to -40. Standard engine oil turned to sludge. Fuel lines froze. Schilling developed a procedure using preheated oil and modified fuel mixtures. It worked. She researched high-altitude performance. Late-war Spitfires were flying at 35,000 feet, where the Merlin engine struggled in the thin air. Schilling developed altitude-compensating carburetor modifications that improved power output by 8% above 30,000 feet. She even developed a power-boosting modification for the P-51 Mustang, making it fast enough to catch and shoot down the V-1 cruise missiles attacking London. Her personal life remained separate. She had married George Naylor in 1938. He also worked at the RAE as an aerodynamicist. When war started, he volunteered for RAF Bomber Command. He flew Avro Lancasters with 625 Squadron, completing 31 combat missions over Germany. He earned the Distinguished Flying Cross. Schilling understood bomber loss rates. 1 in 2 bomber crew members didn't survive the war. She worried every time he flew. He beat the odds, returning to Farnborough in 1944. They never talked about his missions. He never asked about her projects. They kept work and marriage in separate compartments.
When the war ended, Schilling stayed at the RAE. Engineering was her life. In 1948, she received official recognition. King George VI appointed her an Officer of the Order of the British Empire. She wore her formal dress to Buckingham Palace, accepted the medal, posed for photographs, and went back to work at Farnborough the next morning. Her career continued for another 21 years. She worked at the RAE until 1969, a total of 33 years of continuous service. She never reached the top administrative positions. Those roles, in that era, were reserved for men. The RAF leadership structure simply didn't promote women to director-level posts, regardless of accomplishment. Schilling accepted this. She preferred hands-on engineering anyway. Her post-war projects were cutting-edge. She worked on the Blue Streak missile program, Britain's first ballistic missile, designing its fuel delivery systems. She was involved in the investigations into the mysterious de Havilland comet crashes. She researched wet runway braking effects for jet aircraft, publishing 3 technical papers on how water on runways affected tire friction. She even helped design a bobsled for the Royal Air Force Olympic team. It was a strange project, but bobsled design involved aerodynamics, weight distribution, and friction management, skills Schilling had mastered over 30 years. She retired in 1969 at age 60. She spent her retirement restoring vintage motorcycles, occasionally racing at classic events, and maintaining her beloved Norton. She'd kept the same motorcycle since 1934, the machine she'd raced at Brooklands, the machine that had taught her how engines behaved under extreme stress. Beatrice Schilling died on November 18, 1990, at the age of 81. The obituaries in British newspapers focused on the restrictor, the little brass washer, Miss Schilling's orifice. Everything else she'd accomplished, the missiles, the V-1 interceptors, the jet-age safety research, was a footnote. Her legacy lived on. In 2011, a pub in Farnborough was renamed the Tilly Schilling. The Brooklands Museum purchased her racing trophies. In 2019, Royal Holloway University opened the Beatrice Schilling Building for electronic engineering students. The restrictor itself became a teaching example in engineering schools worldwide. A simple solution to a complex problem. Immediate implementation under wartime pressure. Measurable, life-saving results. A small brass washer in a museum case. A reminder that elegant solutions don't always require complexity. They require a brilliant mind that sees the problem and a courageous heart that dares to fix it.